All right, so this is like, I think, the last regular class. The material we finished today, we're done, okay? Yeah, wow. Wow is pretty crazy. So I am recording. I did remember to do that. Let me share my screen. And this last section, this last chapter that we're talking about is about equilibrium. And we can have two different kinds of equilibrium. We can have static equilibrium and dynamic equilibrium, okay? And the static equilibrium has to do with objects that stay still, okay? And dynamic equilibrium are objects that are moving. But the whole idea of equilibrium means that the net forces and the net torques on the object are zero. So we can kind of go back to Newton's first law, which says that an object in motion will stay in motion, an object at rest will stay in rest unless acted upon by a net external force, okay? So if there are no net external forces, then the object just keeps doing what it's doing. And the chapter that we are looking at is concerned with objects that stand still and do what they are doing. Okay? So those criteria for equilibrium are that F net is equal to 0. And because I've drawn F net as a vector, that means that F net x, F net y, and F net z all have to be equal to 0. Okay? And then we also say that tau net is equal to 0. And because I don't specify a particular axis, that means that tau net has to be 0 around all axes, which can be a useful way of solving problems, because I can put my axis of rotation wherever there are a whole bunch of forces that I don't know, and then I kind of eliminate something that I don't know from my problem. Okay? So this should all kind of seem familiar because we did this all before. And I had to look at somebody's notes because I couldn't remember where we were, but I think we're up to the ladder problem. All right, we finished the one with the sign. Okay. All right. So a uniform ladder of mass m and length L leans at an angle theta against a frictionless wall. If the coefficient of static friction between the ladder and the ground is mu, what is the minimum angle at which the ladder will not slip? Okay. So I have my ladder here. And it has some length L, it's got a mass m, and it makes an angle theta with the ground. Okay. And you may very well have lived through a problem like this. Have you ever tried to take folding chairs and lean them up against a wall? Okay, you know, like you're at some event at your church or your synagogue or whatever, and they want you to clear all the chairs, and they start to fall down. Okay, that's what this problem is what's the angle that you have to have it at so that it's all going to stay there and you can pile up a whole bunch of chairs. Okay. So I need to know what theta is. I'm going to need to have equations that have theta in it. Okay. But basically, because my ladder is just going to sit there, my ladder is going to be in equilibrium, which means I can use my criteria for equilibrium, which means I probably want to start by drawing what? A free body diagram, okay? What am I going to draw the free body diagram for? The ladder, okay? So here's my ladder. What kind of forces are going to act on my ladder? Okay, so there's going to be a gravitational force. And because this is a uniform ladder, that gravitational force acts in the center, on the center of mass. Okay, we'll talk about that a little bit more later today. Okay. What other kind of forces do I have? What is that, Fiona?
Normal.
A normal force from what?
From the ground.
Okay, so I've got a normal force from the ground. That's going to point up. So I'm going to call that, I think I called it end floor, actually. Okay, what else do I have? Dagny.
And wall.
Okay, I've got a normal force that comes off the wall. Even though this is a ladder, none of our rules change. The normal force is still perpendicular to this surface of the interface. Okay, Lauren. There is a force due to friction. Okay, friction due to what? What two surfaces?
The ladder and the ground.
The ladder and the ground. And then which way does that friction force point?
To the right.
Okay, this way?
Yes.
Okay, so that's going to be my friction force. Is it going to be kinetic? I'm sorry, yeah, kinetic or static? Static, because I want it to stay, I want my ladder to stay, okay? And my ladder would slip if there was no friction force. It would slip out and down, so the friction force always points in a direction that opposes the motion. Dag.
I was just wondering why there isn't a friction force in the wall.
Because we are told specifically in the problem that the wall is frictionless. Okay. So, you know, in the real world, yes, there could be a friction force there, but it'll make the problem more complicated than you can probably handle. Okay. All right. And I do still have down here, this angle theta between my ladder and the friction force is still going to be theta, because the friction force is going to go along the surface of the floor, because friction forces go along the surface. Okay. All right. We good? Okay. So let's just add in some axes here. The axes aren't really all, I mean, it's important which directions they point, but whether it's plus or minus doesn't matter, because everything should hopefully add up to 0. So the easiest thing in the world is to try to do F net equals MA, because I don't have to do any extra work. I'm just like collecting things. Okay, so let's start with that. Do you want to start with X or Y? Okay, so F net X, that's going to be equal to 0. That's one of my criteria for letting things stand still. So I add up all my forces in X. So I have the normal force from the wall, the static friction force, and those have to add up to 0. So normal force due to the wall, positive or negative? Negative. Friction force, positive or negative? Okay. So that basically tells me that my friction force is equal to the normal force from the wall. Now, what's our formula for friction force? USN, but that's actually equal to what, Annabelle? USN is equal to what? Not in this problem, but in general. Is it just equal to the static friction force? The answer is no. Because the static friction force a fixed thing, right? Because I could push on the table with this tiny little force and nothing happens, and I could really push on the table and nothing happens. So what is mu SN equal to? The maximum static friction force, okay? And I haven't written it that way yet. We've just written that it's the static friction force. I keep forgetting to put this in. Okay. But the problem has what I would identify as a superlative in there. minimum. You have the problem written down, don't you? Okay, so find the minimum angle at which the ladder will not slip, which probably means that I want to take advantage of the maximum static friction force. So it's going to be okay to use Annabelle's formula of USN when I'm writing down the formula for the static friction force. Now note that the normal force that I use is the normal force at the point where the ladder is touching the ground, where the friction force is. Okay, so that normal force is NF. It's not NW. Okay. All right. So this is lovely, except that I still have a whole bunch of stuff that I don't know and I still don't have data. Okay, so next step. What should I do next?
Net Y.
Okay, let's try F net Y. So I've got F net Y is equal to 0. And I'm going to write down all my forces in the Y direction. So I've got that normal force from the floor and the gravitational force. Normal force from the floor, positive or negative? Positive. Gravitational force, positive or negative? Okay. So that tells me that the normal force from the floor is equal to Fg, which is equal to mg. And I can substitute that back in over there. So I can say that US mg is equal to n wall, which is lovely, but I still don't have a theta. So what am I going to do? Torque. Okay. Does everybody have this written down? Okay, because I want to move back up and look at the picture. Okay. So let's remind ourselves for the moment. Okay. Well, what you remind me, what's torque equal to?
0.
Net torque is equal to 0, but what's the formula we use for torque in general?
R cross F.
Okay, so R cross F would give me that. And what's the magnitude of the torque then? Okay, so RF sine phi, we usually say. Okay, so if I did some torques, then I could get theta into there. Okay. So if I'm going to do torques, I need to have an axis of rotation. So where should I put my axis of rotation? Okay, down here? Why would you put it there, Lauren?
Well, I was thinking that way, that has the most forces acting on it, so the torques resulting from those forces would be 0, so then we could only have to find the torque from N wall, and gravity, and that way we can plug those back into the equation.
Okay, so I have no idea what NF, I guess I know what NF is, but I don't know what all those torques are. But I do have an expression for the torque from the wall. So by putting my axis of rotation where NF and FS are, those are effectively going to have torques of 0. So I'm kind of eliminating what they are from my picture, and I can focus on some other torques that I can easily identify. Okay. So let's just remind ourselves here about alternating interior angles and note that that's going to be a theta. And then what's this angle here going to be between the ladder and FG? 90 minus theta. Okay, just so that we kind of have those in our heads. And let's see. Can I actually what? Okay. All right, so there we go. So I just copied my picture over. You were able to see many things at once. Okay, so we're going to do tau net is equal to 0 about the axis indicated in my picture. Okay. But we should still write all of the torques down, even though some of them are going to go away. So I just start at my axis of rotation and go along my object and write down the torque that goes with every force that I have. So like we explained, the torque due to the normal force from the floor is 0, and the torque due to the friction force is 0. And those are both because they have moment arms that are equal to 0. They're acting on the axis of rotation. Okay. Gravitational torque. Is that going to be positive or negative? What? Okay, because it's going to pull my object how? Clockwise or counterclockwise? Counterclockwise, right? From your perspective. I could do it over here. Right, here's my axis, it's going to pull, so it's pulling it clockwise, and clockwise is negative. Okay. So my torque due to gravity is going to be negative. How about the torque due to the normal force from the wall? I'm going to pull this way, and my object is going to move what? Counterclockwise, which will be positive. So just as a practical thing, you have to have some positive and some negative torques, or they won't add up to 0. So if all of your torques are positive or all of your torques are negative, you've done something wrong. Okay. So I'm just going to jump ahead to saying that my torques are equal to each other, because it just makes everything easier. Okay, so the torque due to my normal force from the wall is going to be RF sine phi. What's R? L. F is that normal force due to the wall times the sine of what? Theta. Okay. Gravitational force, again, going to be RF sine phi. What's my R? L over 2. My force is Fg, and then it's the sine of 90 minus theta. Okay. So I could start just by getting rid of those L's. I know what NW is, right? What is it?
S times the NF.
Which is what?
NG.
Yeah. Okay, so we've got USMG is sine theta times sine theta. It's going to be 1/2. FG is obviously mg. And then what's the sine of 90 minus theta? It's the cosine of theta. Okay. That's an important trick. So let's take a little aside for a minute and talk about that trick. Okay, so here's my right triangle. Here's theta. Here's 90 minus theta. Here's A, here's B, here's C. Okay, so sine theta is equal to what? What is it? B over C? What's the cosine of 90 minus theta? B over C. Okay. I wish someone had taught this to me this way instead of making me memorize all those things and they tried to do something really wacky and use double angle formulas. And if they just made a simple right triangle and labeled all the sides, it would have been like, well, oh, of course. But anyway. Okay. So, too far back, too far forward. There we go. All right. So this is great. I need to find theta. So again, I can cancel my mg's. Now I do have a sine theta and a cosine theta. But what if I divided both sides by cosine theta? What would I get? Tangent theta, right? So I could have tangent theta is equal to 1 over 2 mu, and I think the problem just called it mu. So we can say that our theta min is the inverse tangent of 1 over 2 mu. Okay? We good? You understand how we got here? Dead. Okay. All right. So if everybody's good with this, then we want to move on to a new category of problems, which has to do with tipping. Okay, we can also think of it in terms of balancing things. So we could say tipping or balancing. We'll do one example of each. Okay. And this involves talking about something called the center of gravity, which is sometimes COG, sometimes it's CG. And the center of gravity is the point on the object where FG acts. So for a uniform object like a ruler or, I don't know, a pipe, okay, or a box, for a uniform object in a uniform field, so really the important thing is in a uniform gravitational field. Each piece, each part of the object experiences the same gravitational pull. Okay. So in a uniform gravitational field, each part of the object experiences the same gravitational pull. And that implies that the center of mass is in the same place as the center of gravity. You live in a uniform gravitational field. The field pulls the same way no matter where you go. Is it going to be a tiny bit less if you're in Denver than if you're in Florida? Yeah, because your elevation's a little bit bigger, but we're talking about a difference in the hundredths place, if that, maybe the thousandths place. So it's really not that big a deal. You effectively live in a uniform gravitational field, okay? So your center of mass is the same as the center of gravity. And that's why no matter what kind of object I throw up in the air like that, it's going to pivot around its center of mass, and the center of mass is going to be the point that makes the parabola. Okay. A counterexample to that is being near the surface of a black hole. Surface. Okay. A black hole has different, because a black hole is so massive, the gravitational pull from it changes. So if you were to go in feet first into a black hole, the pull on your feet is going to be a lot different than the pull on your head. You get spaghettified, as it were. That's actually a technical term. Okay. So that's not a uniform gravitational field. And we can't say that your center of gravity is not going to be the same as your center of mass. We won't be dealing with problems like that. Okay. So for our situations, the center of mass will be the same thing as the center of gravity. Okay, make sense? All right, so let's try the example, the first example, which says a uniform cubical crate is 0.750 meters on each side and weighs 500 newtons. It rests on the floor with one edge against a very small fixed obstruction. At what least height above the floor must a horizontal force of magnitude 350 newtons be applied to the crate to tip it? Okay. And this is example what? 4. All right. So we've got the ground. We've got our crate. And then we've got some little obstruction. All right, so I've got my crate. I have my obstruction. If I push down here, am I going to flip over the obstruction? No, I'm pushing really hard and nothing's happening. Okay, if I push here, am I going to go? Here? Ooh. Okay, it's starting to move. Okay, so you can see, I hope from that, that it is important where you're pushing. Okay, anybody ever use one of those dollies? It's got handles, and then there's like a flat thing at the bottom that kind of tapers to something really narrow. You stick it under a box, and then you put your foot on the pivot and you pull it back. Okay, depending on the size of your object, you have to pull higher up. You have to have a higher dolly. And that's kind of the same idea as you're changing your torque and the amount of force that you use. Okay, and that's what I'm changing here, believe it or not, is where I apply that force to my object, it's a different torque, and it matters whether or not I'm going to be able to tip my object. Okay, make sense? Understand where we're going? Okay. So it says I want at what least height. Okay, so that's again a superlative. So what I'm really looking for is like that minimum height, okay, that I'm going to apply my force at. Whoops. There it is. Okay. So we're going to start by drawing a free body diagram. Okay, so once again, there's my crate. And because this is a uniform crate in a uniform gravitational field, Fg is going to act in the center, at the center of mass. And then I'm going to have some applied force that's going to act at some height h. And that h is the thing that I'm trying to find. Now, I know this isn't the perfect free body diagram because I'm drawing the forces a little bit different, but I think it's important that you see where that force is kind of pushing it. Okay. When my object is on the verge of tipping, okay, everything is concentrated along that side, that edge that's next to my obstruction. So when it's on the verge of tipping, that means that the normal force is concentrated right there because the rest of the object isn't really in contact with the surface anymore. And there's going to be some contact force from the obstruction. It's going to push back on it. And while I want the net torque to be just barely greater than 0, if I'm looking for that least height, I can figure out where tau net is equal to 0 and then know if I push any higher, I'm going to be moving. Okay, so we've done this, we've used this technique before. So I hope you can tell by now that if I use F net equals 0, that's just going to tell me that the force of the obstruction balances the force of the applied force, the normal force and the gravitational force are going to balance, but it's not going to bring me in H in any way. Okay. So that what I'm really going to need to do is apply the net torque. So where shall we put our axis of rotation? Probably down here in the corner. Okay. Again, I don't really know what the obstruction force and the normal force are going to be. Okay. So let's just get rid of them. But I know what the gravitational force is, and I know what that applied force is going to be. Okay. So this is going to give us tau net is equal to 0. And again, I'm just going to write down all of my possible torques. I have a torque from the obstruction, a torque from the normal force, a torque from gravity, and a torque from the applied force. And then because the torque from the obstruction and the torque from the normal force are acting on the axis of rotation, their moment arms are 0. And so they're going to go away. Okay. So my torque due to gravity, is that going to make my object move in the positive direction or the negative direction? Negative, right? Because again, here, let's put this up here so we can look. Here's my object. My gravitational force is going to make it rotate this way, okay? Which is clockwise, which is negative. My applied force is going to make my object rotate this way, which is going to be in the clockwise direction and which is going to be positive. So we're going to have negative tau g, positive tau applied, and that's going to tell us that the torque due to the applied force is going to have to be equal to the torque due to the gravitational force. Okay. Now we're going to have to go all geometry. Okay, so let's take a little side trip over here. Again, I have my crate. Remember that my crate is 0.750 meters on a side. Okay. And my applied force acts up here at some height h. Okay. And we're going to say that that's some distance, little r, from the axis of rotation. This is my axis of rotation. Okay. So I kind of need to find two things here. I need to find r, and I need to find this angle phi. Right? Okay. And I don't have to know exactly what they are, but I need to know what they are in terms of h. Okay. So again, the beauty of geometry, alternating interior angles. This angle down here in my triangle is also phi. Okay. And so the first thing I'm going to think about is, because of the formula for torque, I'm going to want to know what sine phi is. So in terms of my triangle, what's sine phi? H over R. Okay. Now, it's okay if it's in terms of H. I don't know what R is. Can I find out R in terms of H and the side of the crate? Right? H is the hypotenuse of my triangle. Okay. Or I can remember that tau A is going to be R FA sine phi. Right? So that's going to give me R. I know what FA is. Sine phi is H over R. And what happened to my R's there? They cancel. Okay. So that's going to tell me that tau A is that applied force times the height. Good with that. Lauren.
Is this because when you take your cross product, with the side you only look at the
I can't hear you.
Sorry. Is this because the cross product, when we look at the diagram, we only distance from the axis of rotation to the force would be that's perpendicular to the force. So.
Oh, yeah.
Okay.
Yeah,
so
the math is, yeah, the calculus is bearing that through, yes. Okay. All right, so that gives me tau A. So now we got to look at tau G. So again, here's my crate. Okay, here's my FG acting in the middle. Again, my axis of rotation is over here. So again, this is going to be my R, as in RF sine phi. And that's going to be my phi. Okay, we good? All right, so again, we're going to place, so again, let's write it this way. I know that tau A is going to be R FG sine phi. And I need to find all those things. Different R than from the last part of the problem, but R nonetheless. Okay. So let's call the side of this thing, actually we'll call it L, just because L is nice. Okay, we'll call it L. Now, if FG acts in the middle, what's this? What's the length of that side of that triangle made out of black and red lines? L over 2. And what's this leg of my triangle? L over 2. So again, the sine of phi is going to be equal to what from my triangle? Yeah, L over 2 over R. So again, even though I could figure out what R is, because this is a right triangle, I don't need to. So I've got my tau A is going to be R, FG, sine phi is L over 2 over R. My R's cancel. And we end up with, and in fact, I don't even need to make it mg because I happen to know what the weight is. So I get FGL over 2. You didn't let me on. Okay, we good? All right, so back to the problem, which says that tau applied is equal to the tau due to gravity. So tau applied was the applied force times h. Tau due to gravity was the weight times L over 2. And this we can really easily solve for h. FGL over 2FA. And that gives us 500 newtons. The side is 0.750 meters over 2. I think the applied force was 350 newtons. So what's H equal to?
was just going to one. So good.
I think we are 2. Let's say 2. And in fact, there probably should have been 3 because there probably should have been like decimal points at the end of the 500 and the 350. But sometimes I forget when it's second. So what do you got?
0.54 meters.
Yes. I don't know why. Fiona was nodding her head. Everybody else? Okay. All right, so we got one more problem to do, which I love because it's my favorite problem. What? It's my favorite problem from this chapter, and it borders on my favorite problem of all. Like it's in the top 5. Okay? Because it's something we can actually do, and it kind of sort of almost works. Which is like the best part, when the physics in theory actually kind of does like what it's supposed to do. So, you have 4 identical bricks. These are not really identical, but they're pretty damn close. Okay. So, 4 bricks of length L, identical and uniform, are stacked on top of each other. You have a picture, right? In such a way that part of each brick extends beyond the one beneath. Find in terms of L the maximum values of A1, A2, A3, A4, and H such that the stack is in equilibrium. Okay. These are our bricks. We will calculate how far out they extend, and then we will actually do it. Okay. Now, the trick here, and this is actually why we do this problem, is that to be stable, the center of mass of whatever is above can't be over the edge of the thing, can't be over the edge of the thing below it. Okay? So the center of mass of the bricks above can't be beyond edge of brick below. Okay. So just to start this off nice and easy, this is a uniform meter stick. Where's the center of mass of this meter stick? In the middle, right? At 50? Okay. So if I want this to balance on the desk, okay, that center of mass, that 15-meter part, has to be on the desk. If I put it out here, it's not going to work. So the minimum place that I can put it and have it be balanced is right there on the edge. Okay, so that's the important part, is that if you don't want something to tip, the center of mass has to be over the thing underneath it. Okay, which is also a big part of falling, right? When you start to fall, like I tripped over my dog the other day, because like she was over here and then she decided she was cutting in front of me. Okay, so when you start to fall like that, the thing you're trying to do is to get your body under your center of mass. Okay, and that's why you fall over, is because all of a sudden your center of mass isn't over the rest of you. And that's why you step back, to bring part of your body underneath your center of mass. Okay? Make sense? We understand? All right, that's really the whole point of the problem, is that if you're asked to balance things on the AP exam, you understand that the center of mass has to be where it has to be. Okay. So you have the picture, but I'm just going to draw it real quick so I can point at stuff. All right. Oops, that's really not very good graph form. So here's brick 4, brick 3, brick 2, brick 1, and then these are A4, A3, A2, and A1, and H is adding all of those together. Okay, so like we said, let's start at the top and find A1. So the center of mass of brick 1 can't lie beyond the edge of brick 2. Okay, So this needs to be the center of mass of brick 1. And you can just draw on the picture that you have. Okay. So how much of brick 1 can extend out over brick 2? If the length of each brick is L, we just did it. L over 2, half of it. Okay. Because that's the only thing that's above. No matter where I put that top brick, whether it's on top of 4 other bricks, whether it's on the edge of the table, half of it can extend out beyond the edge of the thing below it so that its center of mass is there. Okay. All right, A2. Now things are a little more complicated. Okay, so if we're going to look at part B, I've got more objects now in my system. And I have to find the center of mass of the system of brick 1 and brick 2 and make sure that it doesn't go any farther than the edge of brick 3. So I'm going to draw a little picture here. Okay. Here's going to be brick 2. Here's going to be brick 1. I know that this distance here is L over 2. And I know that these are my center of masses. Okay. So the center of mass of brick 1 is at L. The center of mass of brick 2 is at L over 2. Right? So my X center of mass is going to be the mass of 2 times its position plus the mass of 1 times its position divided by the total mass. Okay. So if you squint your eyes and do the math, that tells you that the center of mass of brick 1 and 2 together is at 3L over 4. So that means that 3L over 4, as measured from the back of brick 2, needs to be over brick 3. So that tells me that A2, the part that can hang over, is L over 4. So if I put this, okay, here we are, that's 25. I should, and it doesn't really work because things end up getting wacky. But I should be able to put that there. Okay, and it's not quite at the 50 mark because I know it won't really work if I do, because they're not really uniform meter sticks, okay? But I can do that. And then the table is now brick 3. Okay, if I move this out farther, the whole thing falls over. Okay. The table also doesn't exactly have a nice edge. Okay. All right. So now, so I know this is L over 2. This is L over 4. And now I want to find what happens when I've got 3 blocks or 3 bricks. Okay. Well, I've got to draw another free body diagram. Sorry, that's not true at all. I've got to find the center of mass again. So here's going to be brick 3. Here's going to be brick 2, and here's going to be brick 1. Center of mass of brick 1 is going to be here. Center of mass of brick 2 is going to be here. Center of mass of brick 3 is going to be there. Okay. Center of mass of brick 2 is L over 2. Brick 3, I don't know what I said. Center of mass of brick 3 is 3L over 4. Center of mass of brick 1 is 5L over 4. Okay, go ahead. What's up?
For the center of mass of brick 2,
Mm-hmm.
would 3L over 4 be the center of mass of the system of both 2 and 1?
Nope.
Okay.
Nope. And it's because I know that this distance here is L over 4.
Oh, right.
And
Okay.
so it hangs over by that much.
Okay.
I mean, you can do it that way, but that's not what these numbers are going to represent. You can say, here's the center of mass of block 1, 2, and then add to that block 3, but I'm not going to do it. Okay. So again, I want to find the center of mass. So there's block 3, there's block 2, there's block 1. And if you find a common denominator and all that jazz, you get 5/6 over L. Okay. So 5/6 of my lower brick has to be over the brick underneath it. So that means that A3, the part that can hang over, is L over 6. Okay. So if I do this again, and a 1/6 is what, 0.17?
Right. 0.167.
Okay, so we'll go with 0.17. All right, so that's like 17 centimeters. So this part has to be here. What was the one for the one above it? 25, right? So this is going to go like this. Hasn't tipped over yet. Okay. Like I said, they're not perfectly uniform. All right, so for part D, we're going to do the same thing again. Anybody want to guess where the center of mass for that 4-block system is going to be? That's how much I'm going to be able to have left over is L over 8. The center of mass is going to be at 7/8 L. Okay, you can do it yourself, because as it is, I'm just kind of going through the math here. But the pattern holds up. A4 is going to be L over 8. Okay. And an 8 is going to be 0.125. So we're going to go with about 12 centimeters. $17 centimeters, 25 centimeters, I'm cheating a little bit, but
That's so cool.
okay, but it pretty much works. Okay, so the last part is to add them all up. You can do that yourself. Okay, but the other bottom line, aside from the fact that you have to have the center of mass at the edge, at minimum at the edge of the thing below it, is that whole Roadrunner cartoon where Wile E. Coyote hammers in the plank, walks out to the end of the plank, hammers in the next plank. Okay, that's impossible. It's an important thing to know that that is not physics, okay, because he would just fall. Sophie.
Can you apply this to like making bridges?
Yes, and I'm sure you do, depending on the kind of bridge that you're making. Okay. So again, when you're stuck on a desert island someday, you need to know how to do this. And where to put your supports, because if I put a pylon here, I could do all kinds of different things because I have another support that my center of mass could be over, which is why it depends on what kind of bridge you're making, suspension versus whatever the other one is. Okay? So this is the end of chapter 12. Woohoo. Okay? This is the end of the new material. We will have class tomorrow via Zoom, and we will go over the spring break work. If I can figure out what it was, I'm sure I have an answer key somewhere. And then on Thursday, we will start reviewing. Okay? Because we've got, I think, 2.5 weeks. There will be homework on this, but I'm not sure there's going to be a test, so we'll see. Okay. All right, so go be free, eat lunch.